Now, before we start this question, just a small bit of background on statistics in the Leaving Cert. So the early chapters of statistics usually cover this kind of stuff, sampling, stem and leaf graphs, which are kind of just recap over junior cert stuff, really. Then you have your scatter graphs and correlation, line of best fit, that sort of thing, which is purely Leaving Cert stuff, Leaving Cert higher level stuff that you do need to know, but it doesn't come up a huge amount. But it is definitely worth knowing. But the big part of the Leaving Cert higher level course is your inferential statistics. Now, this slide will just cover basically an overview of this. Don't get too overwhelmed by it. But the fundamental part of inferential statistics is your measures of location, and that's just a fancy word for your averages. And even if we were to be more specific, it's mainly to do with the mean. Okay, mode and median do come up, but you need a deep understanding of what the mean actually does for you. Right. Similarly with measures of spread, which another word is variability, but the big one, and like range and interquartile range are ones you would have learned in junior cert, but its standard deviation is the one that we're most concerned about. Another recap of junior cert would be histograms, right? So frequency distribution tables is also on the junior cert course. The shape of distribution, that's also mentioned in junior cert, but all of that leads towards normal distribution. Okay, now when you combine all of these three things, the mean, standard deviation, and normal distribution, you get two extremely important rules, and that's the empirical rule, and most importantly, the central limit theorem. Now, the central limit theorem has three main applications. That's percentiles or z-scores, the 95% confidence intervals, and p-values. And when you combine those three things, right, then you get what's called hypothesis testing of sample mean. Okay, so all of that leads down towards this. Okay, now the interesting thing is that completely separate to all of these is another type of hypothesis testing of the sample proportion. Okay, now the good news is that the approach to both of these is almost exactly the same, but the challenge that you're going to have is just distinguishing. Not only do you have to distinguish between, these three types of questions here and all of this stuff up here, but you also have to distinguish, are we being asked about a sample mean, or are we being asked about a sample proportion, right? But don't get too overwhelmed by that. It will make sense when we see the questions. Now, just a very brief recap on how percentiles and z-scores work. Okay, now, if you're a bit uncertain, or if you're very uncertain about z-scores and percentiles, you're not going to learn it in this slide, but just a very quick recap just to remind people. If we're looking for the area indicated here, here, or here, okay, we already have the z-score. Okay, but to get the area or the percentile, you just need to figure out, we all know that each z-score has a corresponding percentile in the log tables. You know that page in the book, but you just need to figure out, is it the exact number from the log tables that you're taking, or is it 1 minus the number from the log tables you're taking? I'll show you what I mean. So in this case, it's going to be the exact number from the log tables that corresponds to 1.6. But when it's greater than a positive z-score, it's going to be 1 minus the number that corresponds to 1.2. And when it's less than a negative z-score, again, it's going to be 1 minus the number from the log tables that corresponds to 0.2. Okay, now you could go into a lot more detail about why that is, right? And I urge you to do so, but just if you just want a shortcut as to how to calculate percentiles, it's either the number itself from the log tables or 1 minus the number itself in this case. Now, the big important one, and the one that relates to this question, is what happens if it's between two z-scores. How do we get that percentile, right? And again, another little shortcut. You could do a long version of this, but another shortcut to doing this is you just get the number less than the first z-score, which is the one directly from the log tables. You get the number less than the second z-score. So if this question was just like this, the probability that it's less than minus 1.2, right? Well, you'd go to your log tables, you'd find 1.2, the number that corresponds to that, and you do 1 minus that, and you'd get this z-score, right? And to get the probability between these two things, you simply take one from the other, okay, which comes out as that. Now, that's just shortcuts. Now, if you're very uncertain about these, there's no way you learn all of this just by listening to what we just discussed there. But that's just a shortcut for getting each of these. Now, A part 1 in this case, and straight away, it should be clear to you that we're dealing with a z-scores question here. The probability that the patient will wait between 30 and 40 minutes before being seen by a doctor. And look, we have all the information up here. Right? We have the mean, we have the standard deviation, and that should be screaming out at you that it's a z-score question. Now, the first thing I'd always say to people in this case is list out the important piece of information. Right? The mean is 34, standard deviation is 8, and the pieces of data that we're worried about in this case is 30 and 40. Okay, now the next thing then I'd suggest to people is just draw a very quick diagram, right? Just so that you know what your percentile is going to end up looking like. Now after that, then you follow simple steps. Your first step is we want to get the probability that it's less than 40. Then you want to get the probability that it's less than 30, and we're just going to subtract one from the other. Okay, so again, those steps then should be very straightforward for you. So first up, we get a z-score for 40. So in here, into our z-score formula, it's going to be 40 minus 34 over 8, which is 0.75. And if we go to the log tables then, the probability that it's less than a z-score of 0.75, and that's that z-score here, 0.75, probability, and we're looking in the log tables, that number corresponds to all of this area here. Okay, and that's 0.7734. We do the exact same thing then for 30. Okay, now the problem with 30 is that it's a negative z-score. So when we get the number that corresponds to 0.5, it's 0.6915. So because it's less than a negative z-score, it's 1 minus that number, which is that. And to get the probability that it's between here and here, we simply subtract 1 from the other, which comes out as 0.4649. Now this question really would be a very standard question. Okay, whereas this one down here is a small bit more cryptic, right? Because they mention things called upper quartiles. Now, upper quartiles would be big in the junior cert course, right? And also be big in the Leaving Cert ordinary level course, but they're not much seen in the higher level course unless it's something like this. Now, the key to this is you realizing that the upper quartile is the top 75% of the data. Right, that's what, like, the median is the middle 50%, the upper quartile is the top 75%. So it's up to you straight away to be able to translate this into that we want to find the z-score that corresponds to 75% of the data. Okay, now the key here is that 75% is our percentile. So if we were looking at this, we were looking for the percentile, okay, in this first question. Right, whereas in this case, we're given the percentile and we're working backwards to get the z-score, and then we're going to be working backwards again to get the actual piece of data. All right, so that's the key to this question. It's a very common type of question that does come up quite a bit. Okay, so we have the percentile, right, and it's always good to draw it then as well. So this is our percentile, and we're looking for the z-score that corresponds to 75% of the data. So all you're doing is you're going to your log tables, and instead of, like the usual way is that we have the z-score and we look for the corresponding percentile. But here we want a percentile that corresponds to 75%. Now if you look very closely, 75% is not exactly 75%, but this is probably the closest one. Now if you pick this one accidentally or this one, like it's you're not going to lose marks over that. But I'm going to pick this one. This is the closest one to 75%, which is 0.68. So that's the key to this. The z-score that we're working with is 0.68. Now, if you look at how we got this z-score, like in the previous question, right? So it was the piece of data that we're looking for, minus the mean, divided by the standard deviation, gave us the z-score. So we're doing the opposite now, right? We're working backwards to get the piece of data, right? So that is x, whatever this piece of data is, minus 34 divided by 8 will give us an answer of 0.68. So it's just a simple algebra equation that you need to solve, right? So cross multiply by 8, add 34 to both sides, and we get 39.44, which is the upper quartile for this set of data, and it roughly translates as that 3/4 of the patients are seen within 39.44 minutes. Now part B then should be immediately obvious that it's a hypothesis test. Okay, now it's a hypothesis test of a standard of a mean. You can see the key words in there: mean, standard deviation, and really when you see these, you should be delighted when you see them, because they're routine questions. They're difficult enough at the start, but like once you're prepared for these, there should be absolutely no problem. And when you're doing these, I would always suggest at the very start, list out exactly all the important pieces of information. Okay, so and let's use this to actually explain what's happening here, right? So the clinic are saying, their claim is that the mean waiting time is 34 minutes. Okay, and we always have to be given the standard deviation then as well. So that's what the clinic are saying, right? Whereas this nurse has done a study with 100 patients and she found the mean to be 35.7 minutes. Okay, and these are the 4 important pieces of information that we're going to use now. So we're going to use all of this to test whether what the clinic are saying is correct or whether what the nurse is saying. We're not saying that the nurse is correct, but has the nurse proved that the clinic is wrong in what they're saying? Right, but this is always a good start to start it off. Right, now, the interesting thing about hypothesis testing is that there's 3 ways of doing it. Okay, and in this case, they actually don't tell you which way to do it. Right, so it's up to you which way you want to do it. And probably the most common way of doing it is using what's called a 95% confidence interval. So what I'm going to do in this case, there's 4 formal steps that you need to go through in a second, but I'm just going to do the math side of it first, where I'm going to get the 95% confidence interval. And again, this is a very routine thing. The first thing you do is you get the standard error of the mean, okay, which is this formula in your log tables, 8 divided by the standard deviation divided by the square root of the sample size, which is 0.8. And to get the 95% confidence interval, we multiply this number by 1.96 and add and subtract it from the population mean. Okay, so there's your confidence interval, your 95% confidence interval. Okay, now what that roughly translates as, well, no, it's what it translates as, is that if what the company is saying is true, and if you did a sample of 100 people to test this, then we can be 95% certain that whatever you get should be between these two values here. So you should be already noticing that this number, which we haven't used yet, but this number is outside it. Okay, but no spoilers just yet. So now we go through the hypothesis test. And these 4 steps are essential, and this is what the marking scheme is looking for. So your step 1 is your null hypothesis, and this is essentially what the clinic or the company sometimes what the original claim is. The original claim is that the waiting time, the mean waiting time, is 34 minutes. Now the alternate hypothesis then is the opposite of this. Some people make the mistake of saying it's something to do with this, but no, we don't care about this. We just want to prove what the company is saying is wrong. So the alternate is that the mean waiting time is not 34 minutes. All right. So then we have our step 2, which is just writing out the sample mean. No calculations there. And step 3 then is where the maths happens. So that's where you put your confidence interval. Now, if you want to, you can put all of this in here as well. Some people do the calculations in here, which is fine. Step 4 then, again, some people have a bit of a challenge with this, is what is our conclusion now? Okay, so the key thing is that the sample mean, 35.7, is outside, it's outside this confidence interval, right? It's out here somewhere. So therefore, we have enough evidence to reject the null hypothesis. So the waiting time is not 34 minutes. And the key statement there is this: we've evidence to reject the null hypothesis. If you don't mention that, or if it's accept the null hypothesis, then that's what the marks are going for. All right, so very straightforward, small bit of maths, but it's the kind of formal layout of it is what people are looking for. Now, there's a second method then, right, and that's using z-scores, okay, or another way of saying it is test statistics. You see what I mean in a second. Now, the good news about that is that the steps are almost exactly the same, right? You list out your data. It's the same data we're using. The null hypothesis is exactly the same, but the difference here is that instead of we calculate a z-score for this data. Okay, now it's the fancy z-score formula, the one where because we're dealing with a sample of people, it's this formula we use for z-scores. But when you fill those values in there, we get a z-score of 2.125. Now, another word for this type of z-score, when you're dealing with a sample, that z-score, another word, is a test statistic. And that's your step 2 in this case. Instead of just listing out the sample mean, we list out the test statistic of this data. Okay. Now, the good news about this is that the 95% confidence interval in this case is always the same. It's always plus and minus 1.96. And straight away, because 2.125 is outside the confidence interval, similar to the last way we did it, that's why we reject the null hypothesis in this case. So 2.125 is outside the standard interval, or outside the confidence interval, so that's why we reject it. But again, you have to have that statement in there: reject the null hypothesis. Now, the third way of doing a hypothesis test then is using p-values, and interestingly, that's what they ask for then in part 2. Okay, so it just says find the p-value and explain what it means, and that's quite a common question, actually, getting you to explain your understanding of a p-value. Okay, but the good news about getting p-values is that the first 2 steps are the exact same. So your first step is laying out all your information, which is exactly the same in the previous case. Now the second step then is the test statistic that we already found, okay, which is 2.125. Okay, and probably the only thing really that you need to be aware of for p-values is the final step. So the first thing you do is you find the percentile that corresponds, so percentile from that page in your log tables, then that corresponds to 2.125. That's the first step. So get the percentile less than 2.125, and then you fill it into this formula. Okay, so, and this formula is not in your log tables, it's just something you need to learn, right? So it's 2 multiplied by 1 minus that percentile from your log tables. Right, so that's how you get a p-score, right? So the percentile from your log table is 0.9834, so it's 2 by 1 minus that, which ends up as that. Okay, now some people learn that a different way, and whatever way you want to do it is fine, but I think that's the simplest way of doing it. 2 minus 1 multiplied by 1 minus that percentile, and that's your p-value then. Right, now having the p-value is one thing, but now we need to explain what the p-value means. Okay, and look, there's numerous ways you can do it. Now this is just one way that I would do it. Okay, so the p-value of 3.32. This implies that if the null hypothesis is true, so what they were saying earlier, then the probability of getting a mean of 35.7 is 3.32%. So that's a rough way of explaining what a p-value means. The probability of them, the clinic, getting this information, and you doing a study with 100 people and getting a mean of this, the probability of that happening is 3.32%. That's what a p-value does. And the threshold then for whether a p-value is significant or not is 5%. So because it's less than 5%, we deem this statistically significant. So that would be a perfect solution, answer to explaining that p-value. Now these last two questions they're a bit of a challenge in fairness. Now, but it's good to go through them because the key to these questions is figuring out what are they actually looking for. Now that's not actually very obvious in this because they go on about doctors. Okay, but interestingly, if you look at it, you should be able to spot that this is a percentiles question. Okay, so something to do with z-scores, but it's one of the ones where they give you the percentile first. Okay, now in your head you're thinking, right, when in those questions, the traditional way is that, okay, we're looking for a percentile and we're given the population mean, a piece of data to investigate, and a population standard deviation, and we combine these three things to make a z-score, and the z-score then gives you the percentile, right? But it's one of those questions now where you're given the percentile first, and we're looking for one of these three things. Now usually it's the piece of data that we're looking for. But what you'll find interesting here is that we're actually given the piece of data in this case. We're also given the population mean in this case, because they say that remains the same. So the only thing we're actually looking for in this case is the standard deviation. Okay, so it's a working backwards question with percentiles, but it's I've never seen any other question like it where we're actually looking for what standard deviation will give us a percentile of 95%. Okay, now maybe when you do the question it'll become clearer. So first thing we do anyway is, all right, what z-score gives us a percentile of 95%? So that's going to your log tables, looking for the z-score that corresponds to 95%, and it comes out roughly as 1.96. So now we sub all of these three things and this into the z-score formula, okay, which is this, and we want to know what standard deviation gives us a z-score of 1.65. So this is our equation here. Okay, so now we just do a bit of cross multiplication, multiply across and divide by 1.65, and the standard deviation comes out as 6.67. So if we now look at the question again, basically what it's saying is that if the doctors want 95% to be seen in 45 minutes, they will need a standard deviation of 6.67. Okay, now where does all this stuff about new doctors come in? Well, the original standard deviation is 8. Okay, the desired standard deviation is 6.67. Okay, now if we subtract, that's an improvement of 1.33 minutes. Okay, and it's saying that and this is where it just gets even more confusing again, that every 0.4 minute improvement will require one extra doctor to be employed. So if there's 1.33 minutes, you simply divide 1.33 by 0.4 and we get that. Now you can't hire 3.33 doctors, so we have to round that up. So when we round it up, if they hired 4 doctors, well, that would improve the standard deviation by 6.67 minutes. And if the standard deviation is 6.67, then that would mean that 95% of patients will be seen within 45 minutes. All right, so it's a bit of a mouthful, obviously, but it's good to see just how these type of questions are asked and how would you approach that question. Now, finally, we have another challenge here, all right, and this is arguably even more challenging than the previous question because they're moving away now from the sample mean to a sample proportion. Okay, so it's the same data, same 100 patients that we're talking about, but now we're on about the proportion of patients ages 60 or over, which wasn't mentioned before. Now, if you remember, the way we get a 95% confidence interval for a sample proportion is using this kind of formula here. Right, so that confidence interval, we need to find the sample proportion, and we need to add and subtract 1.96 times the standard error of a sample proportion. Right, now this formula here is in your log tables. Okay, so we need the sample proportion, fill it into this formula, multiply it by 1.96, and then we add it and subtract it. Okay, now you need to be quite good at that on its own to be able to figure out, to be able to have any clue about this question. right? Now, if you don't know how to use this, if you don't know how to use this formula, again, there's no point really going near this question. But if you're really well prepared, you'll realize that this is now another one of those questions where you're working backwards. Okay, because now look at this sentence here, because this sentence is a bit mad really, right? So she found that the largest value of the radius, right, where are they getting radius from, of the 95% confidence interval is 9.48%. Okay, now that's just a fancy way of saying that this value was 9.408%. So 1.96 multiplied by the standard error comes out as 9.408. Okay, now that's quite a challenging way of expressing that. Okay, and you'd have to be a real top student to spot it. But this actual question is quite a common question, right? Where you're given the size of the confidence interval and you're working backwards again to try and figure out the proportion size. Okay, and that's essentially all we're doing here. We're trying to figure out what value for p will give us a value of 0.9408. So this is the actual formula or equation that we're trying to solve. Now you'll notice that the sample size is 100, because from the very original question in part B we had a sample size of 100. So we want to know what is the value for p. So we sub it into this formula. Now just follow this now, because the algebra even in this is quite challenging, right? So we divide by 1.96, square both sides to get rid of that, and interestingly here, okay, multiply both sides by 100, but when we multiply out this bracket we get a form of a quadratic. Okay, so there's your quadratic equation. So where are quadratics coming into it? Who would have thought it? Now we use the minus b to do that. I assume everybody's able to do that at this stage. And you get your two values here, which is 0.64 and 0.36. Now if we just go back now and figure out what does all of this mean. So it's kind of hard to kind of figure out what that means, but basically there's 100 people in the study. So if 64% of those, or if 64 patients were 60 years or older, then we would get a standard error of 0.09408. Okay, but also if 36% of them are 60 years or more, we'd also get the same answer. Okay, so it's a very difficult one to kind of get your head around really, but it's just the point of it is that type of question is quite common. Sometimes is where you're given the standard error, you're given some element of the confidence interval, and you're working backwards to get a value for p. Or sometimes, more commonly really, it's you're working backwards to get a value of n.